Hello again, everyone. So today I am focusing on developing the equations and code in Matlab for a simple spring ordinary differential equation. I'm going to, on this little section of the video, focus on the derivation of the equation and writing it in a form that Matlab can work with. But it's worth pointing out that for take-home problem 4, you don't need to do that. The equation has been derived for you. You have everything you need. Even so, I think this is instructive and helpful to understand how to write it in Matlab. So, for a simple spring problem, we have a mass in a position, it's connected to a spring, and there's an inherent damping force. The forces that act on the mass are the restoring force, which has a magnitude of k times x. The formula here is negative kx, and I'm going to explain that just a little bit. X here is measured from the neutral position. It's evident from this equation that when x is 0, there is no force. So that's called the unstretched length, where the spring is happy, and if the thing was sitting there, it would just stay there, because no forces would act. The negative sign indicates that if x is positive, then there's a force that points in the negative direction that pulls it back to its original position, and if x is negative, then this term is positive, meaning that the force will act in the positive direction, trying to move x back to its original position. This force is called a restoring force. It always points towards x equals 0 and always causes the object to accelerate towards x equals 0. The second force is the damping force. Just a little notational point here. As a reminder, x dot is the same thing as writing dx dt. Instead of prime, we use dots for specifically derivatives with respect to time. So x dot, which is dx dt, also has a force in the damping case. This is a force that points opposite the velocity. It's negative bx dot. The magnitude is b times x dot, and the negative sign indicates that it points opposite the direction of velocity. So if you're moving forward, it will cause you to accelerate backward, and if you're moving backward, it will cause you to accelerate forward. This force just slows you down. That's its general purpose. If you have a velocity, it slows you down. And the faster you're going, the bigger the force is. It's proportional, and B, the damping coefficient, tells you how large that tendency to slow down becomes. If we apply Newton's second law to this equation, the sum of the forces is equal to, well, in this case, negative kx minus bx dot. Those are the two forces acting. And Newton's second law says the sum of the forces is equal to mass times acceleration. In this case, there's only motion left and right, so the acceleration is the rate of change of x velocity, which is x double dot. If I then rearrange to solve for x double dot, I will have a second order differential equation, k over mx minus b over mx dot. And this is a whoops, that's not an x dot, is it? X dot. This is a second order ordinary differential equation. All right. To write this in terms of things Matlab can understand, we need to write it as a vector differential equation. These are some notes that I'm going to make about how I'm going to think about the solution, but remember that Matlab doesn't actually need all of this. It just needs the ODE. So y, I'm going to call x and x dot, and therefore y prime is equal to x dot and x double dot. To take a derivative of a vector, you simply take the derivative of the individual components, and the derivative of the first component is x dot, the derivative of the second component is x double dot. I'm mixing dots and primes here, and I don't want that to be too alarming to you. I'm going to use primes for the y's always, and I'm using dots on the right side just because they're familiar to me for time derivatives. It's true that this is a time derivative as well, so I could just as well write instead of y prime, y dot, but I'm not sure. I'm used to the normal, let me go back into that. I'm used to the y vector having a prime on it, so I guess that's how I'm going to write it. But either notation is perfectly appropriate here. So y prime is equal to x dot x double dot. Our goal is to describe the derivative of y with respect to only things that are in y. X dot is easy because it is in y. The derivative of the first component is simply y2, the second component of y. X double dot is not in y, so we have a problem there. I keep hitting that instead of the undo button. No, I can't undo. Well, that's too bad. I don't want these arrows plaguing my picture, so I'm just going to go ahead and erase this. X double dot is not in y, so we need to describe X double dot in terms of the things that are in y, which are X and X dot. But that's what the differential equation does. It gives X double dot in terms of X and X dot. So I'm going to write, instead of X double dot, what X double dot is equal to, which is negative K over mx, which is y1, minus B over mx dot, which is y2. And I was attempting to write y2 in the center here with poor anticipation skills. So this is the derivative of the y vector with respect to time. It is in terms of itself, that is the things that are in y. And time is allowed in here, although there is no time in here anywhere. Not a big problem. This is what Matlab needs. We need y prime as a function of t and y, and we have it. That's what this is. It's y prime as a function of y. T is allowed, it's not present, but it's allowed. For the next portion of this video, we are going to be writing this up in Matlab, so stay tuned. Hello, so this is my first time recording. This is on my personal laptop, and I know the microphone quality is low. We're just going to go with what we've got here, and please work with me. Okay, so we have a differential equation that we've developed. The differential equation is based on a spring motion problem. And now we're going to be working on building that up in Matlab. There is a way to write this function in one line because it's rather simple. So the first thing I will do is I will create a I'll create a file where I just do this normally. I'll just create a single function, a single file that both defines the initial conditions and then runs and then plots, and I will use an inline function just as we've done in the past. So for that code, I'm just going to start that with close all, clear variables, and CLC. I'm going to create the function first, so this is called, I'm going to call it f. It's got to be a function of t and y, or else I cannot give it to ODE45. In this case, I know it's a vector, the first component of which is y2, and the second component of which, remember this must return a column, so I use the semicolon rather than the comma, y2 and then negative k divided by m times y1 minus b divided by m times y2. It's clear to me when I write this function that I'm going to need definitions for all these constants here, so I'll just say m is 2, b is 10, and k is 300. I'm not sure what these values are going to look like. I'll plot the results and then change the values and make them how I like them. Generate good plots. We need an initial value for y, and it's important to realize this y naught value needs to be the y vector. The y vector in our example contained both position and velocity, so this is initial position and initial velocity. We can call this x naught and v naught, and then I'll define those things up here. I'm going to go ahead and do that x naught is equal to 1 and v naught is equal to 0. We could also just define those both here, but I kind of want to separate this problem as much as possible. These are our block of constants up here. This is our definition of everything that ODE45 is going to require. So there's one thing left, and that's the t-span. I'm going to let Matlab choose the spacing, so I'm just going to say let's go from 0 to 5. And Matlab will auto-space as it likes. Now it's time for ODE45, so t comma y is equal to ODE45. I need to give it the function, I need to give it the time span, and I need to give it the initial condition. That's it. Matlab can now solve this differential equation. I don't anticipate any errors, although I am definitely fallible here. So what I will do with this now is I will plot the results. Y is going to be a large matrix of values, and I hopefully will recognize that the first column represents the x position, the second column represents the the x velocity. So what I will go ahead and do is plot the x position versus time. So t is the independent variable, and y colon comma 1 is the first column of y. We'll take a look at that in a minute, but I think this plot and this code overall is going to work. Got to navigate to the correct folder again, bit of a bummer. Classes 250, notes and summaries, ODE 45, spring example. Okay, running this code. It's running very slowly, by the way. I have to use the remote desktop since I don't have my own version of Matlab. So we may be kind of, I don't know, practicing patience here. I'm going to go to the main Matlab window so that I can watch it say busy at me. It's pretty fun. If my sample file is any indication, you have the crackling sound of my mic static to keep you entertained during this exciting time. I want to point out this code should run in a very short amount of time. This should not take a long time to run whatsoever. But anyway, here we are. We started at an initial position of 1. We accelerated in the negative direction quite rapidly. We overshot the equilibrium, which is at x equals 0. And we continued to oscillate for a short while and then dampened out. These values kind of show the typical response for a damped oscillation. If you've taken differential equations, you know there are several cases under which this works. This is an underdamped oscillation, and that's fine. I don't necessarily need to change the values of m, k, and b to get some sort of other type of result. This is fine with me. So that's my plot. It's pretty decent. Oops, pardon me. Okay. So now what I'm going to do is make the modification that you will absolutely need to make for question 4. For question 4, the details on the differential equation are far too complicated to write them in a single line of code. So we are going to write a separate function file to do this for us. I'm going to show you a couple of different issues that you can run into here. Spring example function. So I've made a separate file. This is going to be a function file. I'm going to define it, and it's going to be called by my other file in ODE 45. To make a function file in Matlab, what we're doing is setting up a rule between input and output, just like we did in the inline function. To write a function file, we first start with the word function. That's pretty easy. Then what comes next is the variable we're going to use for the output of the function. This choice doesn't matter, but it needs to be referenced later in the code, so just keep track of whatever you call it. I'm going to call this y, because that's a natural choice given this differential equation. We give it dy dt, and it outputs y. For that reason, I'm going to call my function dy dt. That's what comes next. So this is y equals dy dt, and then parentheses, and then the input variables. And in this case, what I'm just going to say is t comma y. This kind of looks good. Y is a function of t and y, but these can't match each other. The input variable and the output variable need to be different values. So I'm going to call this y out, or even y func might be more appropriate. I like that better. So this is the initial, this is a function that we're building, and this is the output. Oh, I suppose I'm a little confused. Let me clarify some things. in my mind, I was imagining that this function outputs y, because that's the solution to a differential equation. And I want to emphasize that is not what this function does, not at all. This is the differential equation function. All it does is it gives you dy dt as a function of t and y. For instruction's sake, I think these are the best names for the variables. This outputs the value of dy dt as a function of t and y. I do not like this name for my function. For naming these files, this is very important. This must match the file name. And a more descriptive name is better, both for your file name and your function name. So I'm going to call this what I've called my file, which is Spring Example Function. The output of this is simply the derivative. The user gives t and y, and what outputs is dy dt. This is what an ODE solver needs. So I'm going to go ahead and just write this out, dy dt. Well, I'm going to show you how we can use multiple things here. So I'm going to say, so the user gave us y and t, so I'm going to make some variables here. I'm going to say x equals y1, x dot equals y2, or you know what, I'm going to call it v. I like that even better. V for velocity or speed, if you like. And now I'm going to just go ahead and say that dy dt is equal to v colon negative k divided by m times x minus b divided by m times v. I can do this because I defined these variables up above. X and v are now known by me because the user gave them in a vector and I put them into these variables so that I could use them. Okay, so that's the entire thing. We're going to get a little warning here that says, hey, it looks like t isn't being used, but that's the nature of this. You cannot get rid of the t because ODE 45 needs it to be there. So we're just going to go ahead and let that be. This gives some good advice. Input argument t might be unused, although a later one is used. Consider replacing it by tilde. That's a good approach. We could replace it by a tilde. That's going to save us a little bit of time. This shouldn't take very long to run anyway, so it shouldn't matter. But this at least is going to save some memory. So that's that. This is the differential equation. Yes, this is the differential equation. We're now going to plug it into this Spring example file. So there's a couple of issues left that we're going to work through one at a time. In this line of code, line 13, we call the function f. Well, now we're going to call the function that we just made, and the name of that function is here, Spring example function. So that's what goes here, Spring example function. This is the name of the function, but it's worth pointing out this is not in our workspace. When we ran this line of code, it was saved to our workspace, so just typing its name worked. This is not in the workspace, so typing this is not going to work. We need to tell Matlab to go searching for it, and that's pretty straightforward to do, fortunately. You just have to put this in strings, and that's going to make Matlab go look for a file with that name. This is recognized to be a function call by ODE 45, so this just says, hey, go look for this function file. This needs to be saved in the same directory as the file we're writing, or it needs to be in the path anyway. So that's what I strongly recommend, to make sure those are in the same file or folder, or else this won't work. I'll run this now and we'll still run into a problem, unfortunately. The problem is that the remote desktop is painfully slow. Now let's see. Busy, busy, busy. Oh, good. Didn't take so long. Undefined function or variable k. It's important to recognize that in a function file, you can't use variables that are defined in the other file. So we have two options. We can either take this block of constants that are used and cut them and paste them over here. This is in general not the best way to do it, and the reason is you don't really ever want to be opening this thing again, and you might want to change these values, right? Like change it to 2, 5, and 20. I don't know. Just change the values to see what the response, if the response is any different. There's lots of situations where we'd want to change this. So I want to be able to create some sort of adjustment that that happens in our, what I would call our main file, this one. So I'm going to go ahead and undo this. I want these to stay here. I want these to change and update, but those variables aren't called for. This is an issue of local memory. So when you're in a function, you only use the functions that were only use the variables that were defined in the function. This doesn't have access to your overall workspace. The exceptions are inputs to the function and global variables. A global variable is one that you specifically call out to say, I want this to be available everywhere. And in this case, this means I want this variable to be available for other files, like functions. Like this is a perfect example of when a global variable might be appropriate. So what I'm going to do in my main file is declare these three variables as global. Global mbk. They'll change a slightly different color. Here I'm going to also call them out as global mbk, and that solves our problem. Now when I run this main file, I will not get that error. Practicing patience again. There's our graph, same one as before. And now in our main file, I can change M, B, or K and just see what the change in response is. I decrease the damping. I get a new plot in time. There it is, less damping, more oscillation, longer vibration. So this is our main example that you can use to build a function file for the differential equation. I want to do one more little thing. How do you use this function file? Well, we don't really need to use it. Matlab uses it here. But if we were to try and use it, what would that be? Like if I say spring example function, and I give it a value of t equals 3 and y equals 4, what will I get? Well, I'll get an error. And the reason is this requires a second index because our function file calls on y too. Well, this is just a single element. There isn't a second element of y. Remember, this is y, this is t. So we need to, when we're typing this out, give it an initial, well, we need to give it two elements, a position and a velocity. So I'll do 2, 3, and this now outputs a result. But my question for you is, what is the result? This says, if you're at a position of x equals 2, v and a velocity of v equals 3, then your current rate of change of position is 3, and your current rate of change of velocity is negative 307.5, which is to say you are slowing down a lot. You are accelerating in the negative direction. Ooh. Let's read this together. Oh my goodness. Okay, well, we'll look at that later. All right, this is position and velocity, their rates of change. You give it t and y, it outputs y dot, and this is what is needed for a differential equation to solve. For question 4 of the take-home exam, this is what you are trying to build. If you build a function that if you give it y, it spits out y dot, you did it. You need to give that to OD45 and let it run. All right, so that'll conclude this video. I will post another video specifically talking about question 4.